So far, this chapter should have been a review of what you learned in a previous class. However, now we're going to talk about something that we did not talk about in that previous class. Something that's a little more complicated, but it's really not too bad. We're going to talk about unsteady flow processes. So processes where the control volume might gain or lose energy and mass. And there are several examples of this. There are several systems that can be modeled as a piston cylinder device, where air, say, comes out or some gas comes out as the piston drops, and therefore the system is losing air. Since that air carries energy, it's certainly losing energy, but boundary work's coming in, so what happens there? We could talk about a supply line where we've got, say, helium at certain conditions flowing through that supply line, charging an initially evacuated volume, a bottle that needs helium charged in it. If you like paintball, you might want to think about a paintball tank being filled by air, right? It's depleted, there's some mass in it initially, but it's not enough to push a paintball out the end of the barrel, at least not if you had fun in the last game, right? So it has to stuff air into this, and usually, you know, at a shop, they'll have a system that's set up so that you can screw in multiple or attach multiple tanks at the same time and charge them all. So it would be a lot like this. It wouldn't necessarily be initially evacuated tanks, but they would certainly be depleted of air. So certainly the amount of mass in that control volume is changing, and the amount of energy in it is changing as well. So there are plenty of examples besides those where unsteady flow processes are interesting and useful and worth consideration. We can look at mass conservation in a couple of different ways. We can look at it kind of like your bank account, really in both cases, but on the left-hand side, we're considering how deposits and withdrawals change your account balance. I don't have to know how much money there is in your account to know that if you deposit $100 and then you spend $200, your account balance went down by $100, and you better hope you had at least $100 in there initially, right? I don't need to know that you've got 1,000. I don't need to go know that you've got 1,000,000. It doesn't matter how much you've got. If you put in 100 and you withdraw 200, your account balance has changed down by $100. In the same way with mass. If I put some mass into a container and I take more out, the difference between what I put in and what I took out is the change in the mass in that system. I don't know how much mass is in the system, but I can certainly tell you the change by the deposits and withdrawals. On the other hand, the right-hand side mass balance equation is kind of like your monthly statement. Have you ever looked at them? You should. It's good if you do. I looked at my monthly statement once and found that I guess I had taken a trip all the way to Boulder, Colorado, and spent $250 or so in a Home Depot and another $250 in a Lowe's or something. Well, I don't remember doing it, so I called up my bank and found out that I was the victim of identity theft. That's the worst identity theft I've ever experienced. I was really upset about it, so I called the police in Boulder, Colorado, trying to say, hey, look, this happened. You've got someone, you know, doing illicit transactions, and they didn't seem to care. That was a little disconcerting. But at least maybe my tally was added to their pile. Maybe they gathered enough evidence that they found whoever was doing it and took care of the problem. But anyway, on the right-hand side, this mass balance is also talking about the change in mass of the system, but it's looking at an initial and final balance. So if you get your statement, say at the end of the month, and the statement says you've got $1,000 in your account, okay? And then next month you get your statement and it says you have $2,000. Obviously, the amount of change in your account balance was $1,000, right? Yeah, there was a bunch of withdrawals and deposits that caused that to happen, but we really don't need to know what they were. It doesn't matter. The point is, you got $1,000 more. This is a good thing, right? So the mass final minus mass initial is considering just what's in the system at different points in time, whereas the mass in minus mass out, those terms are considering flows that come in and leave. Now, since both equations talk about the change in mass in the system, we can set these two equations equal to each other and talk about how the mass that comes in and leaves the control volume causes the mass in the control volume to change from some initial amount to some final amount. And that's what CV stands for, is the control volume. So what we'll usually write is mass in minus mass that exits. E stands for exit, equals the mass in state 2 minus the mass in state 1, where the mass in state 2 is the final mass in the system. The mass in state 1 was the initial. So we knew we had a system that had a certain amount of mass in it, state 1. We let some mass flow in, mi, we let some mass flow out, me, and then that resulted in m2, the amount of mass in the system in state 2. It's a simple idea, it's not too bad. Basically, we just balanced your checkbook, okay? It's just your mass checkbook. Now, what about energy conservation? Well, one of the problems we're going to have with unsteady flow is that we have to assume a uniform flow, not a steady flow in the sense that it's, how can I say this, that it's continuous and will happen forever. That part's unsteady, but we a lot of times will have to assume that the properties of the incoming or exiting stream are constant. Otherwise, it really makes our problem difficult. So if in reality we know that the properties change, like let's say we've got a leaky balloon and air's coming out, but the temperature of the air is dropping as more and more air comes out, what we'll have to do is assume some average temperature and deal with it that way, and just assume that all the air comes out at that one temperature. That will make our lives a little bit easier and will give us a good start at approaching these kinds of problems. So uniform flow, unsteady uniform flow, just means that we assume that any flowing streams have the same properties over time. So if we expand our energy balance, where we're just talking about the amount of energy that comes in minus the amount of energy that goes out, equals the change in the energy of the system, because remember again, the system energy is going to change, well then we can consider the different ways the energy can come into the system: heat, work, and mass flow. Right? Since it's a flowing stream, we need to use theta because it's a flowing fluid. So it has not only flow energy but thermal energy, as well as kinetic and potential, which we usually throw away immediately, but you get the idea. We also have to consider these same things for any mass that's leaking out or flowing out of the control volume. But notice on the right-hand side, instead of just saying m delta E, right? We've got the mass in state 2 times the energy in state 2 minus the mass in state 1 times the energy in state 1, where those energies are specific energies, and notice something else, they are not flowing. On the left-hand side we have flowing streams. On the right-hand side we're talking about a stagnant fluid within the control volume. Therefore there is no flow energy to consider. Okay? So the mass on the right-hand side is mass in the control volume before and after the process, where we've, maybe stuffed some more mass in, withdrawn some mass, did some heat and work, transfer. But in state 2, that mass that remains in the system has a different amount of energy in the final state, which is state 2, than it had in state 1. So notice, again, that theta will include enthalpy, whereas E only includes internal energy. There's no flow energy over on the right-hand side of this equation. Often the kinetic and potential energies are negligible, and so we can write the equation this way, using enthalpy instead of theta, and using U, thermal energy or internal energy, instead of E. And so really the equation I wrote at the beginning is probably not all that useful. The one in the box is the one we really want to use for these unsteady uniform flow types of problems.